So good morning. Just hold on, let me share my slides. I believe you can see my slides. Go on slide show. So you're welcome to my section of CHM 102. We're looking at the determination of the structure of organic compounds, including qualitative and quantitative analysis in organic chemistry. So determining the structure of organic compound is very essential for the understanding of the chemical behavior and the synthesis and applications of such compounds. And this we can do by carrying out qualitative and quantitative analysis, as well as spectroscopic and chromatographic methods. So for the qualitative analysis, we identify which elements and functional groups are present in the compound. And a quantitative analysis, we determine the exact amount of each of the elements in the compound. So the spectroscopic and chromatographic methods also are important to reveal detailed structural features using physical data. All these find application across pharmaceuticals, forensic science, food chemistry, and environmental monitoring. We know that organic compounds, primarily, they contain carbon, hydrogen, nitrogen, oxygen, sulfur, and halogens. So the first step is to carry out the identification of these elements. And so we want to look at using Lassen's test for this. So Lassen's test is a classical qualitative analysis method that is used to detect the presence of nitrogen, sulfur, and halogens in organic compounds. And this procedure involves fusing the organic compound with sodium metal to convert covalently bonded elements into their ionic forms, and then they are extracted and then tested. So to carry this out, first of all, we need to prepare the Lassen's extract. And this is done by just taking a little piece of dry sodium metal and heating it in a fusion tube until it melts to a shining substance. And then a pinch of organic compound is added. And that's the organic compound that you're trying to test. A pinch of it is added. And then a mixture is heated strongly to initiate that fusion reaction. So then the next step is the extraction step. So the red hot fusion tube is plugged into a china dish that is containing distilled water. Then the contents is crushed with a glass rod and then heated to boiling. The resulting solution is then filtered. You filter it to remove the part that is insoluble. And then the extract you then have is what is known as the Lessen's extract. And this is what we're going to use in most of these tests that we're carrying out. So, how do we detect nitrogen? So, we take a small portion of the Lessen's extract, and then we add a few drops of freshly prepared ferrous sulfate solution. Then we heat that mixture, then add few drops of ferric chloride solution, and then acidify it with concentrated hydrochloric acid. Once this is done, you then observe. If you have a Prussian blue coloration, this indicates the presence of nitrogen. And the chemistry behind this is that sodium cyanide formed during fusion reacts with ferrous ions to form ferrocyanide ions. And upon oxidation, these ions form ferric ferrocyanide, which is the particular thing that imparts the Prussian blue color. Now, also, we have to detect sulfur. How do we do this? We still also take a small portion of the Lessen's extract and add few drops of sodium nitroprusside solution. When we do this, if we observe a purple coloration, this indicates the presence of sulfur. The chemistry behind this is that sodium sulfide that is formed during fusion reacts with sodium nitroprusside to produce a purple complex. We still have another test. We have two tests for sulfur. The first one is sodium nitroprusside test, and the second one is lead acetate test. So in this test also, we also take a small portion of the Lessen's extract and then add acetic acid to acidify the solution. Then add a few drops of lead acetate solution. And when we do this, if we observe the formation of a black precipitate, this indicates the presence of sulfur. And the chemistry behind this is that hydrogen sulfide, that gas, hydrogen sulfide gas that is released during acidification, reacts with lead acetate to form lead sulfide, which is the black color. So also detection of halogens. For halogens also, we take a small portion of the Lessen's extract and add concentrated nitric acid and then boil the mixture. We then cool the solution, then add silver nitrate solution. When you do this, for the different halogens, we observe the following. If it is chlorine, we find some white precipitate of silver chloride, that forms, and this is soluble in an ammonia solution. Then that is chlorine that is present. But if we find a pale yellow precipitate of silver bromide, then that is partially soluble and in ammonia solution, then that is bromine. If what we obtain or observe is a yellow precipitate of silver iodide that is formed, which is insoluble in ammonia solution, then that is iodine. And the chemistry behind this is that sodium halides formed during fusion reacts with silver nitrate to form the respective silver halides. But there's something we have to note. There could be some interferences. For instance, the presence of both nitrogen and sulfur in the organic compound can lead to the formation of sodium thiocyanate during the fusion. And so what happens is that this could result in a blood red coloration when ferric chloride is added. And then one can mistakenly think that it's a positive nitrogen test. And so to avoid this interference, sulfur should be detected first before checking for nitrogen. So also it's very important to handle this reaction with care because of sodium metal that is very highly reactive. Okay. So we want to look at qualitative analysis in respect to functional groups. So in this case, specific groups of atoms within the molecules can be determined, their chemical properties, and the reactions of those molecules are unique to those compounds. So various chemical tests are employed to detect the presence of these functional groups. So I'll show you some slides below, the different tests that we can use to identify different functional groups in organic compounds. So for alcohol, the OH group, we have sodium metal test for alcohol. So alcohols react with sodium metal to release hydrogen gas, which indicates the presence of hydroxyl group. Also for alcohol, we can carry out acetyl chloride test. Alcohols react with acetyl chloride to form esters and release hydrogen chloride gas, which produces white fumes when exposed to ammonia. That's for the acetyl chloride test. We can also carry out steric ammonium nitrate tests for alcohols. So alcohols react with steric ammonium nitrate to form a red or pink complex. And this confirms presence of the hydroxyl group. So for aldehydes, the CHO group, we have different tests to carry out. And this one is Tollens test or silver mirror test. Aldehydes reduce ammoniacal silver nitrate to metallic silver, forming a silver mirror on the test tube. Can also carry out Felling's tests for aldehydes. So aldehydes reduce Felling's solution to form a red precipitate of copper 1 oxide. Can also carry out Schiff's test for aldehydes. Aldehydes react with Schiff's reagents to produce a pink or magenta color. So for ketones also, we can carry out iodoform test. In this case, methyl ketones react with iodine in the presence of a base to form yellow precipitate of iodoform. Another test that can be carried out for identifying ketones is 2,4-dinitrophenylhydrazine test. in this case, ketones react with the 2,4-dinitrophenylhydrazine to form a yellow or orange precipitate. And this indicates the presence of a carbonyl group, So now we have carboxylic acid group. In this case, we can carry out sodium bicarbonate test to identify this group. So carboxylic acids react with sodium bicarbonate to release carbon dioxide gas, which turns lime water milky. The other test for carboxylic acid is the esterification test. In this case, the carboxylic acid reacts. Carboxylic acids react with alcohols in the presence of sulfuric acid to form esters, which can be identified by their characteristic fruity, sweet smell. So we have the amines. Also, the amine group can be identified using carbylamine test. Primary amines react with chloroform and alcoholic potassium hydroxide to form an isocyanide or carbylamine, which has a characteristic foul odor. Then also another test is diazotization test. Diazotization test. In this case, aromatic primary amines react with nitrous acid to form diazonium salts. And these can be further reacted to form colored azo compounds. We also have in-space tests that can help us to distinguish between primary, secondary, and tertiary amines. So now for phenols also, we have some tests. Example, the ferric chloride test to identify this group. Of course, phenol group is the OH group that is attached to aromatic ring, that is phenol group. So phenols react with ferric chloride to form colored complexes, often violet or purple, indicating the presence of phenolic group. We can also use Lieberman's test to identify hydroxyl group, phenolic groups. Phenols react with sodium nitrite and sulfuric acid to form colored complexes, confirming the presence of phenolic group. We have esters. So for esters, we carry out hydrolysis tests. Esters react with water in the presence of an acid or base to form alcohols and carboxylic acids, which can be identified by their characteristic smells. And then we have also Z-cell test. So in this case, esters react with hydrogen iodide to release alkyl iodides, which can be identified by their characteristic reactions. So also halides. Halides also. In this case, we carry out silver nitrate test. The halides react with silver nitrate to form precipitate of silver halides, like I showed you on the previous slides, which the silver halides, this can be distinguished by their color and solubility in ammonia solution. The different halides can be distinguished by their color, like I showed you in some slides before. So they can be distinguished by their color and also solubility in ammonia solution. So we also have alkenes. So you can identify alkenes using bromine water tests. Alkenes decolorize bromine water, and this indicates the presence of a double bond. We also have Bayer's test for alkenes. So alkenes react with potassium permanganate to form a brown precipitate, indicating the presence of a double bond. So the alkynes also, how do we identify? So we carry out bromine water test also for alkynes. So alkynes decolorize bromine water, indicating presence of triple bond. And Bayer's tests also, alkynes react with potassium permanganate to form a brown precipitate, indicating the presence of a triple bond. So we want to look at quantitative analysis, estimation of elements, quantitative analysis. Remember, quantitative analysis will enable us to know the exact amount of the elements present in that compound. And so in this case, we're looking at Liebig's combustion method. So, and this method was developed from the 19th century by Justus Liebig. It's a classical technique for quantitative estimation of carbon and hydrogen in organic compounds. So we use this method to estimate carbon and also hydrogen in organic compounds. This method involves complete combustion of a known amount of organic substance in excess oxygen, combustion of a known mass of organic compound or organic substance in excess oxygen. And this leads to the formation of carbon dioxide and water. So the amount of carbon dioxide and water produced are then measured and then can be calculated to obtain the percentages of carbon and hydrogen in the sample. So let's see how we carry out this Liebig's combustion method. We have some apparatus here. I mentioned that it is for carbon and hydrogen. So we have the combustion tube, we have the platinum boat, we have the cupric oxide, we have oxygen supply, we have U-tubes, two U-shaped tubes connected in series. The first one containing anhydrous calcium chloride to absorb water vapor, and the second one containing potassium hydroxide to absorb carbon dioxide. So this is the procedure. You can just follow this procedure, weigh the combustion tube and the U-tube separately, place the known mass of the organic compound into the platinum, and then carry out the combustion. Insert the platinum boat into the combustion tube, add a sufficient amount of cupric oxide around the sample, connect the combustion tube to the U-tube, and then you pass your oxygen and to ensure complete combustion. And as the combustion occurs, then we have carbon dioxide and water being formed. So the carbon dioxide is absorbed by the potassium hydroxide solution in the second tube, while the water is absorbed by the anhydrous calcium chloride in the first tube. So the next thing is to weigh, get it cooled, weigh the tubes and determine the mass of the carbon dioxide and the mass of the water. Then next thing is to carry out your calculation. You know your mass of water, mass of the organic compound as W, mass of water that is formed as X, mass of the carbon dioxide formed as Y. So you also know that 1 mole of carbon dioxide contains 1 mole of carbon atom. So the molar mass of carbon dioxide is 44 grams per mole. The molar mass of carbon is 12 grams per mole. Therefore, you can calculate the mass of your carbon as follows. So just put in your value and then you get the mass of your carbon. So for hydrogen also, 1 mole of water contains 2 moles of hydrogen atom. So the molar mass of the water is 18 grams per mole. That of hydrogen is 1 gram per mole. So you use this formula here to calculate and get the mass of your hydrogen and then the percent hydrogen in that compound. So we can also estimate nitrogen. So we use Kegel method, which was developed by John Kegel in 1883, long time ago. And this method involves digestion of organic compound, organic nitrogen compound into ammonium sulfate. Then the next thing is distillation and then titration to quantify the nitrogen content. So a known mass of the sample is heated, and then you add concentrated sulfuric acid. That's the digestion, often in the presence of a catalyst like cupric sulfate. So that will convert the nitrogen into ammonium ions. Next thing is the neutralization. So what you've digested now is neutralized with a strong base. Typically we use sodium hydroxide, and this will release ammonia gas. The next thing is distillation. The ammonia gas is distilled into a known volume of standard acid. Standard acid used example is the boric acid solution. Then you carry out the titration with standard base, sodium hydroxide. And then you can carry out your calculation as shown here. Your V here is the volume of your acid, N is normality of the standard acid, and then W is the weight of the sample. So you can calculate the nitrogen content. Advantages, this particular method is that it's widely accepted and standardized method. It's suitable for a broad range of organic materials. Limitations are that they're time-consuming and the labor-intensive. Hazardous chemicals are required. Specialized equipment required. And it's not applicable for compounds with nitrogen in certain structures like in azo and nitro groups. So another method you can use for estimation of nitrogen, the second method is Dumas method. So in this case, this method involves combustion of a sample in excess oxygen, converting nitrogen into nitrogen gas, into nitrogen gas, which is then quantified. So the procedure is carry out the combustion of a known mass of the sample at a very high temperature between 800 and 900 degrees centigrade in a combustion chamber that contains hydrogen. Then the gas is collected. The resulting gas and gases are passed through a series of columns to remove carbon dioxide and water. Then the detection. Remaining nitrogen is measured using thermal conductivity detector, TCD. Advantages is that this is very rapid. You can get results in minutes. It's fully automated, and it doesn't require hazardous chemicals. Limitations are that its equipment is very costly at initial stage, and then not suitable for samples with high fat contents due to potential fire hazards. And another one is that it requires calibration with standard materials. Okay, so we can compare Kegel and Domas methods, as you can see here. You can take time and look at them, I've mentioned, and the different processes, so you can compare, you can see the different methods here compared. And then also we can estimate halogens also using Carrier's method. The sample is heated with fuming nitric acid and silver nitrate in a sealed tube. Halogens precipitate as silver chloride or silver bromide or silver iodide, and then it is weighed, and you can get the percentage composition. So another one is estimation of sulfur and phosphorus. The quantitative estimation of sulfur and phosphorus compounds. It's very important, so you know the compositions, and then particularly in the analysis of proteins, fertilizers, and pharmaceuticals. There are two classical methods that are used here. We have the Carrier's method and the sodium fusion test. So for sulfur, the Carrier's method involves the oxidation of sulfur to sulfuric acid, and then followed by precipitation as barium sulfate. So a known mass of the organic compound is placed in a sealed Carrier's tube with fuming nitric acid. Tube is heated to oxidize the sulfur dioxide. And then after cooling it, barium chloride is added to precipitate the barium sulfate. And the precipitate is filtered, washed, dried, and weighed. So you can calculate it using this formula. You know the atomic mass of your sulfur, and you know the molar mass of your barium sulfate, and you put it in and calculate it. The second method is sodium fusion test, which involves fusing the organic compound with sodium metal to form sodium extract, which you then test for sulfur. And this is how you carry out the calculation also. Then you estimate phosphorus as well. You can use the Carrier's method also for the estimation of phosphorus, oxidize phosphorus to phosphoric acid, and then precipitate using ammonium phosphomolybdate. So, and then you get your precipitate filtered, washed, dried, and weighed, and then you follow this calculation procedure and obtain the phosphorus. Another method is magnesium phosphate method for determining the phosphorus in the organic compound. And in this case, you heat your organic compound with fuming nitric acid to obtain your to oxidize your phosphoric acid. And then magnesium mixture is added to precipitate magnesium ammonium phosphate. Then the precipitate is ignited to form magnesium pyrophosphate, which is then filtered, washed, dried, and weighed. And you can calculate it using this formula, noting the atomic mass of your phosphorus and the molecular mass of your magnesium pyrophosphate. So we have a summary here of the different methods. This is a summary at a glance for those different methods. Now let's look at the empirical and molecular formula. So the empirical formula is calculated from percentage composition. It shows the simplest whole number ratio of your atoms, while the molecular formula requires molar mass that is obtained via mass spectrometry. So you divide your molar mass by your empirical formula mass, and then you get to multiply subscripts. So we have example here, empirical formula, CH2O, molar mass, 180. Your molecular formula is C6H12O6, the glucose. And also structure elucidation techniques here. So we use the spectroscopic method to actually reveal the structure of your compound. And so here we use infrared spectroscopy, which measures the vibrations of bonds under IR, under infrared radiation. It identifies your functional groups by characteristic absorption bands. So you have the wavelengths where different bonds, where they absorb. So the OH bond absorbs between 3,200 and 3,600 wavelength. So, and the COO bond is 1,700. The NH bond, you can see the different bonds and the wavelengths. And then you see their characteristics: broad, strong, sharp, and so on. Within which functional groups you can identify within what wavelength. Okay. So also we have nuclear magnetic resonance spectroscopy also, that also helps to provide information on the structure of the compounds. It shows how the position of a signal in the NMR spectrum correlates with the type of proton that it originates from. And then you have your mass spectrometry, which measures mass to charge ratio of ionized molecules, and it provides molecular weight fragmentation pattern. So the key data here, you have your molecular ion peak, which gives molar mass. You have the base peak, give most intense and useful for identifying common fragments. And then you have your isotope peaks, like halogens showing distinctive patterns in the peaks. Now we also have UV spectroscopy, and it examines electronic transition in conjugated systems. So the more conjugated the system is, the higher the wavelength. And this indicates the presence of chromophores, color-forming compounds, and the extent of the conjugation. So you have here, it also indicates the presence of different orbitals here, the pi orbitals, the transition of the different orbitals. When you have the pi orbitals are bonding molecular orbitals that are formed by the overlap of p atomic orbitals. And you have your the pi excited pi orbital as the antibonding orbital that is formed by overlap of p atomic orbitals. The n orbitals are non-bonding atomic orbitals. They're often containing lone pair of electrons. So you have your transitions involving the movement of an electron from one orbital to the other. So you have your chromatographic techniques that are used for separation, purification, and analysis of organic compounds. Here you have example of the thin layer chromatography, where you spot sample on silica plate, and then it is developed in the solvent, and the components move with different retention factor values, and you have your retention factor equals to the distance moved by compound divided by the solvent front. Just like this example, you see you have the solvent front there, and you have the distance moved by the compound. You can see the mixture A and B, and you see the different compounds separated, and you see the solvent front. So you can calculate your RF value from there. We have gas chromatography, which is used for volatile compounds. It provides retention time and purity. And you have your HPLC, the high performance liquid chromatography. It's used for polar or thermally unstable compound. It has high resolution and very good for complex mixtures. So the systematic approach that is used for structural determination is what I'm showing you here now. First of all is elemental analysis. You know the percentage composition, you know the empirical formula, and then you know with the mass spec, you're able to know the molecular mass, the molecular formula. And then with the IR, infrared spec, you're able to know the functional group, identify the functional groups. With the NMR, the framework of carbon and hydrogen atoms. With the mass spec fragmentation, this supports backbone structure. UV will detect the bonding conjugation, and then the chromatography for purity and purifying mixture and carrying out analysis of mixtures also. So To conclude this, classical and modern techniques complement each other in determining the molecular structure. And qualitative analysis detects elements and functional groups. Quantitative analysis gives exact percentage of elements in the compound. And spectroscopic techniques provide detailed structural information. Chromatography assists in purification and mixture analysis. And then mastering all these techniques is very vital in chemical, pharmaceutical, and forensic fields. So I'll also suggest some books for you to read: Morrison and Boyd, Abia Labman, and then Vogels. You can still read this, and it will be very useful in giving you good understanding of this topic. So thank you. I want to stop sharing my slides here. Thank you. And see you in the next class. So